a demo of Lab 4 1.1 in which we create an experiment in DETR connected with 1 MB per second link and with a round trip delay of 25, and then we use iPerf in TCP for throughput and UDP mode for maximum bandwidth. So we created a basic NS file with the same specifications, 1 MB and 1.5 one-way delay, so 25 round trip delay, and we'll swap the experiment in to start the experiment. I will pause the video till the experiment swaps in and then open PuTTY terminals on the two nodes, node A and node B, and create a UDP server on one and a client on one, and same way create a TCP server and a TCP client. So I'll pause the video here and continue with the PuTTY program. Alright, so we'll create the server on node A and we'll create the client listening to the UDP server with a bandwidth of 100 KB P. Wait for the results. Alright, so there has been a loss of 2.2%, so let's just ping it once more. So for 100 KB per sec, it is 2.2, but on an average on 102 KB per sec, the packet loss is 0%. Let's ping it once more. Again at 102, it becomes 0%. Now let's create a TCP server. TCP port and a TCP client. Do not specify the bandwidth for TCP. Yes. So it is 1.19 megabytes at the throughput of 992 KB per sec. Let's do it once more. This time it is 935 KB per sec when our specified bandwidth in the NS file is 1 MB. So this concludes the first part of the Lab 4 demo. Thank you.
Hi. To create 1 gigabit LAN between node A and B, the NS file will provide it. So we'll set the link between these two nodes A and B. It has been shown with capacity 1 GB. So we'll set the LAN for node A and B with 0 ms delay and 1 GB capacity. So after modifying the NS file, we'll swap in the experiment. The experiment has been swapped in. Now we'll try to check the delay between node A and B. For that, we used to log in into the PuTTY using our Data Lab account. So basically, we are performing this experiment for creating up a LAN connection between node A and B, and to check how much time it usually takes to connect between any two nodes. For that, we need to log in inside node A and B. So we'll copy the qualified name and SSH inside that node for node A and for node B. So we can ping any node to any node to check the delay. If we ping from node A to node B, the time usually comes as 0.243, 0.162, but the average delay is 0.198 or 0.20 milliseconds. But in this case, we have used the default window size. Now we need to perform iPerf in UDP mode to measure the bandwidth delay product. For that, we need to go inside our Emulab directory and then perform iPerf. So we need to create one server and one client in this case. We'll use node B as a server and node A as the client. We need to define the port number as well for the server so that client can connect to that port number. In this case, the UDP buffer size is 41.1 kilobytes. Now we'll try to connect this client to port number 5000. So we have not defined bandwidth or window size in this case. Let's see what ideal case we get for 0%. So as we can see, for 0% we have obtained 0.046 ms delay and 1.05 megabits per second as a throughput. Or we can call it as a bandwidth because we are getting it for 0% link loss. So bandwidth is usually the maximum throughput that we get. Now we can do it for TCP. So the default TCP window size is 64 kilobytes here. We have to check which protocol performs better in this case, TCP or UDP. So as we can see, the throughput obtained in TCP is 884 megabits per second, which is quite large if we compare it to the UDP. We can also do this experiment for different window sizes. This one was for the default size, which was 64 kilobytes. We can perform it for 128 kilobytes as well, but by reducing the window size, as we can see, we have used it was 128, which is very low, so it will give us a very poor performance, which will be approx 10.3 kbits per second. Since it was not declared in kilobytes, so this value was very low. Now we can perform it for 128 kilobytes or 256 kilobytes, so we can also reduce it to 4 byte, 16 byte, whichever you want. And let's see the changes. So in this case, the TCP window size for server was 16 bytes only, and the TCP window size was 32.5 kilobytes. So there is a huge difference between it. Therefore, we can expect a huge delay. Now we can perform it for 128 kilobytes, so 16 kilobytes. So obviously, if we increase the window size, we will get a higher throughput. As we can see, it was 887 megabits per second for 16 KB. Let's see what it will be for 8 kilobytes. For client, we have taken the default window size 32.5 kilobytes, and it was almost similar since we have not changed the receiver or the client window size. So both were 887, 885 megabits per second, so they are quite similar. Now we can see the changes if we modify the TCP window size for the client. So it's been decreasing gradually if we are keeping the client window size constant and decreasing the server window size. But there will be a huge difference if we decrease the TCP window size for client. So initially it was 880 megabits per second, but by changing the client window size, it came out to be 262 megabits per second. From here we can see that there's been a huge difference, and the throughput has decreased a lot because of changing the client window size from 256 kilobytes to 4 kilobytes.
So the next part of the tutorial is to explore the secure copy program application. So it's a simple program that uses SSH, and let's create an experiment to transfer files between two nodes. And yeah, I have it ready with a 0.01 link loss and 100 Mbps link with the 12.5 ms delay. So let me swap in. um, so yeah, I have logged into my Data Lab account using Putty, and I have my notes swapped in. So let me access both of my notes. So when I SSH into node A, and I'm now SSH into node B. So yeah, I oh, it's a typo, sorry. So now I have logged into node A and node B. So let me ping node B to find out RTT between the two links. So I have now pinged node B. Let me stop the ping process. So now you can see that the average RTT time is 25.094. So that can be used for our bandwidth delay calculation of the node. And so as said earlier, the link delay should be set to 0. So now I'm going to modify that. After creating the experiment, we have to set the link node to 0. So I'm going to go into experiment options, modify traffic shaping, and then change the delay to 0 and click on execute. I've given the wrong parameter. Actually it should be 0, just 0. Now you can see that the delays of the nodes have been changed, and so let's get to the next part of the experiment right here. So the link's capacity is 100 Mbps and the RTT is found to be 25.094, and now that's with the ping calculation. Let me try pinging again to verify my RTT. So ping node B. As you can see, ICMP packets are sent again just to verify. For 0 ms delay, we are getting around 0.305, which could be due to the processing delay included in the link. So now to find the bandwidth delay product at 0 delay is bandwidth into delay, which is equal to bandwidth of the link, which is 100 Mbps, into the delay which we got, which is theoretically 0, and practically we find it to be 0.350. Let's include that in the calculation. So that equals 33 kilo bits per second. So that's our bandwidth delay calculation. So now let's get to the mount directory, where we have to create a file of 200 megabyte. So type in the command for making the 200 megabit file, which we will be using to transfer it to node B using the SCP application. So this is the command. It's stored as data.bin Sorry for the typo. So now the file is getting generated, and you can see that a 200 megabyte file has been created. Now let's use SCP to transfer this file, which is at data.bin, to node B. So yeah, it's not user, it's the ID, which is USC542DU. And as you can see now that SCP has begun its file transfer, and yeah, so it's done. And you can see the throughput is 3.5 megabyte per second. 200 megabyte of data being transferred at 0 delay. So that is the minimum amount of time taken to transfer a 200 megabyte file at 0 link loss. Now let me increase the delay to 25 and see what changes do we get. So theoretically, if we increase the delay by exponentially, then if we increase delay linearly, then our throughput decreases exponentially. So let's check whether that is correct or not. So now I've changed my delay to 25 milliseconds. Let me just log out and log in again so that the parameters get into effect to the nodes. So now I'm logging out. So sudo chown user /mount gives permission for file transfers by other nodes to the corresponding node, which is node B in this case. Now let me change the entry to mount and start SCP again. So the same 200 megabyte file is now transferred at 25 millisecond delay. Let's wait and watch to find out how much throughput we are able to achieve. So now it's done, and you can see the throughput is 282.9 KB kilobyte per second, and it's taken nearly 12 minutes for the file to transfer. So from this, it is evident that as delay increases, throughput decreases exponentially. So now let's get to the next part of the experiment, where we try to modify the loss and check for throughput. So as in the case of delay, loss also hinders the throughput of the transfer. So as SCP works on SSH, and SSH in turn uses TCP for its application, there is like a big hit on throughput. So TCP guarantees sequential order of packets, which means that even if one packet is lost by the link, the application has to make sure that it sends everything from the first. So now I have modified the link loss, and let me do the same transfer here to check how much throughput we get. Let me log out of node A and node B again so that this change can be brought to effect. So yeah, I have logged out on both of the nodes, logged in into node B. let me start the transfer again. So the permission command has been given and the scp command shall be started, and let's wait for the transfer to get complete. So as you can see here, I have tabulated the values of throughput for packet loss, and for 0.1 we are getting 6.9, and for 5 it has absolutely hit rock bottom to 0.521. So yep, that sums up the goal of the experiment, which was to analyze throughput with packet loss and delay, and that ends lab 3 video. Thank you.